Alright, this is Mr. Fontenot 1111, and I am working here in Chapter 14, Electromagnetism, of the Groves 2024 Basic Electricity and Electronics textbook. And here's what the cover of that textbook looks like. And in this video I'm trying to show you how to do the Chapter 14 math, the Connect math specifically. So let's look at problem number 1 here. And it says a coil has an induced voltage of 2.8 kilovolts when the rate of flux change is 0.5 Webers per second. Calculate the number of turns. So the formula we're referring to is Faraday's law of induced voltage, and we're going to take this formula and we're going to put it in our formula circle like we've been doing with Ohm's law and the power formula. And we're basically going to apply any algebraic formula, any three-letter algebraic formula can be put into a circle, and as long as you got two, you can find the third. And in this case, we are being asked for here, calculate the number of turns. So N would be equal to the induced voltage divided by d phi over dt. Now phi is our Greek symbol for magnetic flux, which is the strength of the magnetic field over time. And in this case here, and it also says, let's look at the explanation of this formula. First of all, it says that our phi must be in Webers. Now, if you remember from the Chapter 13 formula sheet, there are two measurements of phi. There is Maxwell's and there is Weber's. Well, in order to use this formula, we need to be in Weber's, and luckily it gives it to us in Weber's. Problem number 2, you'll see where we have to convert from Maxwell's to Weber's, but in this one it gives it to us in Weber's. It says Faraday's law of induced voltage states the amount of induced voltage is determined by three factors: the amount of flux, that's the strength of the magnetic field, the number of turns in a coil, and the time rate of cutting. The faster the flux cuts a conductor, the higher the induced voltage. So this is how we're going to use the formula. Our number of turns is equal to our induced voltage divided by our Webers per second. And we see here that we just plug in our induced voltage, which was 2.8 kV, divided by 0.5. Now it gives 0.500, but that's the same thing as 0.5 Webers per second. So when we punch that into our calculator, we see here that we're going to go 2.8 times 10 to the third over 0.5 Webers per second, and we're going to hit equals, and it tells us that our number of turns, our answer, would be 5,600. So basically the question was, if a coil has 2,800 kilovolts, when the rate of flux change is this rate, how many number of turns would you need in a coil to do that? And we just answered that question. Moving on to number 2. Alright, the magnetic flux surrounding a coil changes from 1,000 to 6,000 Maxwell's in 7 microseconds. If the coil has 200 turns, how much is the induced voltage? So in this case, we are looking for induced voltage. So our formula this time is going to be induced voltage. If we covered up induced voltage, if we covered it up with our finger, we would see that it would be equal to the number of windings times d phi over dt. So our induced voltage is equal to the number of turns times d phi over dt. And do we have the number of turns? We do have the number of turns. And that's given to us right here, 200. So that will insert here. Now we need to say times d phi over dt. Now we see here that we go from 1,000 to 6,000 Maxwells. So we actually have a change of 5,000 Maxwells. But remember, our phi must be in Webers. So we're going to have to use a formula from our chapter 13 formula handout, and it tells us that Webers, which remember we have to have Webers is equal to Maxwell's times 1 over 1 times 10 to the 8th. So how many Maxwells did we have? We had a change of 5,000, so we're going to say 5,000. Let me go back up here, and it's going to be 5,000 equals, so it's 50 micro-Webers. I plug in my difference of Maxwells, which is 5,000 times 1 over 1 times 10 to the 8th. That gives me an answer of 50 micro-Webers. My formula is V is equal to N times d phi, which we got that answer now, over dt. And dt was given to us right here, 7 microseconds. So my number of turns is 200 times this converted number of 50 micro-Webers divided by 7 microseconds. And that gives me an induced voltage of 1,428.57142.9 volts. And the book or Connect, the computer system, says 1,429 plus or minus 5%. So that's how we get the answer to number 2.